Good afternoon, everybody. My name is Charlie Nicklin. I'm Chief Executive of IAgrE, and I'd like to thank you all for joining our June presentation. For today's lecture, I'd like to welcome IAgrE member Juan Turrion, who is Head of Strategic Research at Invica Industries. Juan is an agricultural engineer with a PhD in fungal genetics, and he leads innovative work on biocarbon solutions, a subject he's been involved with for over 15 years. As usual with our lectures, everybody will be muted. If you'd like to ask a question, please pop it in the chat at the bottom of the screen. And then at the end of the presentation, we'll unmute you so you can ask in person. Okay, I'll now hand over to Juan.
Thank you very much, Charlie. I will try to share the presentation. Hopefully this will work. Yeah, so today we are going to talk about biochar, like as an agronomic solution. We're going to talk a little bit about how this soil amendment can also help in carbon capture, and it may help us removing atmospheric CO2 and solve global warming problems. So we need to start in some place, and I'm going to start in 1542 with Francisco de Orellana. He was a Spanish explorer and was the first person to cross all over the Amazon River. When he was doing this amazing adventure, he described many cities around the river, great big cities with massive societies and really complex. Then he finished the expedition. He returned back to other lands, and nobody explored the Amazon for other 80, 70 years. And when they returned to the Amazon, they didn't see all these cities. And all of this was forgotten until a few years ago, beginning of this century, the end of the 20th century, when they start to discover these soils that they are lots fertile than the rest of the Amazon basin. These soils, they are called terra petra. Maybe you have heard about them. The translation from the Portuguese is like black earth. And as you can see here in this picture, this is poor guy. This guy is in many biochar presentation. So you have like really dark soils, which are really fertile with massive productions compared to the surrounded soils where crops they're not growing that well, and the soils they are not as dark. So basically, and this is very well expressed in a BBC documentary that I invite everyone to see if they want to go deeper in this topic, called The Secret of El Dorado. It's a BBC Horizon documentary, very, very interesting. And basically, where all these cities that Francisco de Orellana was mentioning is where you can find these soils. And basically, if you see this documentary says that thanks to these soils that the humans modify, applying biochar, they could hold all these big societies. But when Francisco de Orellana was doing this expedition, it spread the smallpox. There was like a population collapse, and that's why these cities were yeah, basically they disappeared. So this is our starting point. The rediscovery of the terra petra soils, adding biochar, it has a solution. This biochar stays in the soil for at least more than 500 years. I will say that even more, because if we go to these caves, like really old caves where we have like the Stone Age paintings that they have 10,000 years, 20,000 years, you still can see, if you go to a museum, you can still see the charcoal being produced from bonfires where the primitive humans, they used to do their activities there. So we have proof that this material that is coming from biomass can stay on soils and on the ground for thousands of years. So to first understand this, we need to understand the carbon cycle. I will go really fast with it. So we have the CO2 in the atmosphere. The plants, they capture the CO2 through the photosynthesis. This CO2 is transformed into other molecules. In this case, for our for the case of the biochar, is the biomass, and we're talking mainly about lignin, cellulose, and hemicellulose. And then these components, they are released back either through the use by humans of this biomass, wood products, paper, and other elements that sooner or later they will be either burned for bioenergy uses, or they will be released by the activity of microorganisms back to the atmosphere. So closing the loop back of the CO2 and back to here. With the biochar, what we are going to do is that we are going to break this cycle. So the plants, they're going to absorb the CO2. 50% of it will be released back to the atmosphere through the plant respiration. 50% it will be stored in the form of biomass. So now what we are going to do here is the pyrolysis, which is the thermochemical transformation of the biomass. So basically, we put the biomass in absence of oxygen at temperatures over 400, 500 degrees. 25% of the original material, so 50% of the biomass, it will stay in the form of biochar, and the other 50% will be released in the form of syngas, that can be used for other carbon neutral uses like production of steam, production of heat. You can go all the way down to the production of renewable energy, and from there to what is called e-fuels and other fancy productions. This biochar could be used in the soils, enhancing the fertility, reducing emissions of other greenhouse gases like nitric oxides and methane, and sequestering the carbon there for thousands of years. The feedstocks that we can use, as I said, there's plenty of biomass feedstocks. We can think about forestry, like logs, but also within the forestry, we have many residues like leaves, residues from the thinning, from cleaning up the forest. Also, we have agricultural biomass, so we can have like secondary crops like maize, in this case, triticale. I think this picture was taken in cereals a few years ago. We have also bioenergy crops like willow. In this case, I put a picture of miscanthus, but also different residues from the pruning of different plants, like in orchards, like apple trees, like vines, olives, anything. And also, you can use greenhouse stacks. A few years ago, we did some trials with pepper residues, so the stacks of the peppers to do some biochar. It did work really, really well. The agro industries are really interesting source of biomass. So we have olive subproducts, like in this case of olive stone, but also the olive cake. In the wine is the same. So we have the wine solid residues, the peels of the grapes, etc. that could be used. Coffee is the same, cocoa is the same, and it's also very interesting the palm oil residues like the palm fruit branches, but also is the PKS, the palm kernels, and another cells from another nuts like almonds and macadamia, for example, and plenty of others. So we have the energy and water sector. Over here we have the biogas digestate, which is getting more and more interest as a biomass source, because so many times you have to do a treatment because you may have plastic contaminations or even PFAS in the case of sewage sludge, and you want to safely decontaminate them because obviously the PFAS, they will be destroyed during the pyrolysis. Is gaining a lot of interest recently, the algae, either seaweed, macroalgae, and microalgae. The seaweed could be either cultivated or even collected in at sea, or the algae that they arrive to the coast, but also cultivated microalgae in this modern projects with people that are trying to grow microalgae, although maybe you need to look for, and I will explain it later, for systems that they will be run not dry, but run it wet. And I will come to that in a second. Also, waste is very interesting for us, like waste wood, garden waste, organic fraction of the municipal solid waste, and many other wastes. So anything with biomass, it can be used in this process. The qualities will be different. That's to be true, and the uses will be different. So in addition to the biomasses, we have different technologies. The most common one to produce pyrolysis is what is called the slow pyrolysis. As I said, is really high temperatures, 400 degrees, 500 degrees, at in the absence of oxygen, and uh, and then you make a retention about 20-30 minutes depending on your process. Also, you have fast pyrolysis that is also more focused into the production of oils, and normally you don't produce any biochar. You have a gasification that improves the production of gases by the reduction of the production of char, and so many times is really high in us, because also you can put some catalyst there, so the ash is very high. And another technology that we are using is hydrothermal carbonization, which it has the advantage that your biomass could be wet. Here I put some samples of a homemade biochar production with what is called an anila stove. Here is the Invica's plant of biocarbon, and this is our plant in hydrothermal carbonization. Also, a very important point is that we need to look for the whole cycle, so not only the production of biochar, but the production of the syngas that will go for heat and power uses. And this is key for the sustainability of the whole process. So the pyrolysis, so what is it? So again, high temperatures, and when you increase the pyrolysis temperature, let's put it here like 200, 300 degrees, and this here like 800 degrees. So what's happened is that the yield is reduced. All the volatiles of the biomass, they are removed. They're going to the syngas, and then it stays like a solid biochar. But at the higher temperatures, the quality of the biochar will increase, the fixed carbon will increase, the heating value will increase, and also the stability of the biochar will increase. Things like, for example, there's analysis that it can tell us how good or bad is this biochar, and I will go in a second, going to go further into this. And one of them is the ratio between hydrogen and carbon. So the lower it is, the higher the carbonization of the product is. But also in recent years, there's another test called random reflectance that is a petrographic analysis and is getting more and more interest. So here in this table, we have the hydrogen carbon contents, and here we have the random reflectance. So anything of random reflectance is a complex methodology, but everything higher than 2%, it will give us a stable carbon. So as you can see, everything below 0.4 hydrogen to carbon, it gives us like a more stable carbon in the form of inerted. So this technology is getting more and more important in recent years, and is given to us the most accurate measurements of the permanence of our biochar in the soil, because obviously we want it to be as long as possible. If you put a raw biomass, maybe it will last you a few years, as probably everybody knows here, through the transformation of the biomass into different chemicals like humic substances, etc. But at the end, they will be even degraded, the humic substances. The biochar, if is really high in inerted, is not going to happen that. as I explained you before. So we have other technology, which is called the hydrothermal carbonization. This technology processes the materials in humid, so it has the advantage that you don't need to spend massive amounts of quantities to dry your biomass, because in the case of slow pyrolysis, it's essential that the biomass will be dry because it's a process that is conducted under dry conditions. Here, because we can process high humidity biomasses, we can process things like food waste. I think in this case, they are like orange peels or residues from the production of fruit juices. Agro waste, like they are really high in humidity, sewage sludge, urban bio waste like garden waste, and even green waste. So we get all these materials, we put it inside the reactor. The reactor is over here. This column that you can see at the bottom. This process goes at really high pressures, 20 bars, 210 degrees. And what you're doing there is that you mimic what's happening in nature. So you have really high temperatures, high pressures, and you mimic the carbon production. So from this process, you obtain two products. One of them is biocarbon, which is really similar to lignite. I would say it's almost the same. And also you produce the wash of some elements that for the biocarbon you are not going to be interested. For example, the potassium, maybe for agriculture you are, but for the biocarbon that could be used in other processes like the steel industry, you are not interested in these chemicals to be there. But for example, the potassium goes to the liquid fraction, which you can be used for biostimulant. So you will have here the nitrogen and the potassium. And in addition to this, you will have some organic molecules with many agronomic interest. Anyway, so you can also produce the biochar with the slow pyrolysis. That's the traditional way to do it. And here I'm going to put a practical example of pyrolysis in an industrial way. So this plant I helped to build 7 years ago. It's a plant that is running with olive cake. It produced 1 ton an hour biochar. So it's fed with 3-4 tons an hour of biomass. As you can see, it's a really long plant where you feed the material, you heat it up, and then you produce the biochar and a gas. And you can see here the gas. In this case, it produced 3 megawatts of steam for the extraction of olive oil, for the chemical extraction of the olive oil. So here you can see when the reactor was installed and then the final production of the biochar. So one of the things that that's happening currently in the biochar world is that we are working in the standardization. So we need a standard just to be to make like an homogeneous process for everybody to understand where we are. Also for the analysis of the biocarbon and the biochar and analyze the quality. So for example, I'm involved in the ISO group TC238, and we are working currently in the biocarbon standard, ISO 17722. And here we are putting the standards for pyrogenic biocarbon. And with the pyrogenic biocarbon, we are including biochar, biocarbon, HTC, or the product of the HTC. We are going to assess it with different properties like the carbon content, the ash content. So, for example, the ash content will tell us what is going to be the final use. The moisture also is important, the stability. This is the random reflectance that I talked to you about. Also, the hydrogen carbon fraction is very important. Also carbon reactivity, like the VT number. So this is the surface of the material, the water retention of the product, and the electric conductivity, which is another very interesting measurement to assess the quality of the product. Also the composition and the calorific value. But it's very interesting to make key distinctions between biochar and biocarbon because so many times when you want to use the biocarbon, for example, to be combusted or to be used as a redundant agent, for example, in the steel industry, the people call it biochar, but it's the wrong term. Biochar is when you want to store the material for hundreds of thousands of years. So when you apply the biochar into soils for agricultural purposes, that's what you can call it biochar. But you can call it biochar when you are going to burn it, either in electric arc furnace to producing steel or for other potential uses. Lately, this very fashionable to also use the biochar for construction products. So you include the biochar in the construction products, which for me is very interesting for materials that you cannot apply to a soil because they are, for example, high in heavy metals or other pollutants. And it's a solution for these other materials from specific wastes. Another thing that is very interesting and is creating a lot of problems, at least for me, in the recent months, is the IMO, the International Maritime Organization. So from the beginning of this year, they have changed the classification of biocarbon from a material that you may have an exception if you pass a self-heating test to don't have that exception. So everything is classified as hazardous material. You need to follow some very specific rules, which are really complicated and make everything very, very complicated. You cannot transport loose. You cannot transport it without any control. So you need very specific control. And currently we are working in a way of how to solve this issue of self-heating of the material. So as I was mentioned before, one of the things that we are doing is that we are using biocarbon for the steel industry. As I said, it is defined biocarbon, no biochar. The idea is to reduce the emissions of CO2 from the steel industry. So basically use the biocarbon, it replaces part of the coke that you're using at the moment. All of this is based in what is called the UK ETS that steel manufacturers they need to pay quantity of money for every ton that is produced. We are also involved in this project, European Horizon project called BioResteel, where we are working on the pyrolysis of HTC material. There's some pictures of our factory. Here is where we produce our briquettes. This is some samples of our briquettes, and this is an export that we did last year of e-coke. So biochar in agriculture, I'm going to stress, I'm not going to get into mm, a lot of detail, but I would like to stress two things. One of them, or a few things. One of them is the importance of compost with biochar. This is a synergic interaction, very important if we want to increase the yields of the products. Um, of our crops. So compost and biochar, they work really well together. I will return to that in a second. Also, people have seen that biochar could work really well in livestock systems, mainly in areas where other methodologies they have difficulties. For example, the reduction of ammonia emissions from animal bedding. So if you apply biochar to animal bedding, you will reduce these emissions, and on top of that, you capture the ammonia in the biochar with the subsequent utilization in the soils for the plants, saving a lot of money there in nitrogen. Also, the biochar, it will help us to reduce the emissions of greenhouse gases like nitrous oxide when you apply to the soil. So this is also very important. But also the nutrients run off. The biochar will store these nutrients in different ways. We can go deeper into that if you want later on. But basically, it's not only the biochar; it's the microbial community that is associated with this biochar, which is key with the biochar and the biochar in the soil. Also, the biochar per se improves the soil health, improves the structure, increase the water holding capacity, which is important in dry climates or in dry years and in sandy soils. It buffers the pH, increase the microdiversity of your soil, and it is applying on the long-term fertility. Biochar has like a catalytic effect in soils. It's not only what it does, but it works like a catalyst in many ways. As I mentioned, one important thing to understand with the biochar and the application in agriculture is the interaction with compost and the organic biomass. When you mix or you co-compost the compost with biochar, you activate the biochar. So the biochar, which is sterile when you produce it, because the temperatures that I mentioned, they kill any microorganism. The biochar is colonized by microorganism and potentiates the actions of the biochar, and this is key. Also, it reduces the emission of methane and nitric oxide during the composting or during the compost storage, which I think is really important, and increase the water holding capacity with all the interactions between the microorganisms and this microbial microfauna. Also increment the soil nutrient absorption with this interaction of the microbiota. But there's a big but here. Current applications, they apply really high tonnage, and I think this is one of the biggest criticisms that I found in the agricultural community. So people that are talking about 1-2 tons per hectare. This is very expensive. Many farmers, they think that it's not financial possible because you're doing an investment for 100 years, 200 years. Many farmers, they are looking at what is going to happen next year. So I think this is one of the problems that has the application of biochar in the real world. And I think the solution, and seeing what is happening lately in the biochar community, is coming through the application of precision agriculture, applying biochar at lower quantities, and instead to spread it in general in the whole area of your field, apply it in the areas when you really need it at really lower quantities. Also, it is needed the adding something else to the biochar. And I'm going to put you an example here. The biochar could be added or could be enhanced with urea. Here I put in a research where they are mixing biochar with urea at different concentrations, and they use different standards, the urea alone. And what they see is that when you mix the biochar with the urea is released more slowly. And this obviously will have effects in your yields and also in the potential runoff of your nutrients. So what it seems is that biochar, it can have other effects that will add value to your biochar. But if we go to the precision application of this biochar, here is one experiment that I did in Spain with 50 kilograms an hour They mix the biochar with urea, producing the effect that I just mentioned of the slow release of urea with time. They co-apply the biochar with the seed, as you can see here. So you can see this is a maize crop. You can see the maize, and you can see the little biochar particles at the same time that they are seeding it. I found this small test that it was done in a few hectares in somewhere in the middle of Spain. Very interesting because they've seen two things. First, they analyzed the vegetation index. This is the sample with biochar. This is the sample without the biochar, as I mentioned to you, with really low quantities. And what they have seen is that the biochar sample they have they have healthier plants. So at the end of the day, when they did they harvest the crop, that was like last autumn, they only found a really small increase in yields. But the most important thing is that they reduced the input of urea by 7%. And as I mentioned, was their first test, like playing around with everything. But this is very important because the farmer for 50 kilograms an hour that maybe will cost them 20 or 30 pounds. So it's not a massive amount of investment. If you apply it every year, you're applying 50 kilograms an hour. In 10 years, you will have half a ton per hectare. And if you do it for 20 years, you have 1 ton an hectare. And you're storing the CO2 in your soil slowly, but with a positive effect and spreading the financial cost. Um, the conclusion that I want to give to you today is that we must place greater emphasis on the substantial agronomic benefits of biochar, such as improved soil health, nutrient retention, and crop productivity, while recognizing that its carbon sequestration potential is a value co-benefit rather than the primary objective. To achieve this, precision agronomical tools, applying the biochar when it's needed, and add value applications like the sample that I put with urea, should be implemented with biochar utilizations for the real implement of biochar in agriculture. And I hope that you like the presentation. I know that it has been brief, but I think I gave a general idea of what is biochar, what can you do with biochar, how can you produce the biochar, and of course we can go here from this presentation to the different branches that they can be developed from that. So I'm open to questions, and again, thank you very much to IAgrE for the invitation and to allow me to show to our community the potential benefits of biochar. Thank you very much.
Okay, thank you for that. Yeah, I'll start the questions. Where I've got a couple of questions really. Where is it currently being produced in the world?
Biochar.
Yeah.
So, for example, a few years ago, the government released a call for atmospheric carbon capture. In this call, I think there were like 5 projects in the UK. I'm talking now about the UK, okay? Where they developed different systems to produce biochar. We were one of the ones selected. So now we're currently producing biochar. It's not a massive plant as the one that I saw you in Spain. But it allows us to do a few experiments. It's only, I think, 400, 500 kilograms an hour. And this other in Spain is 1 ton an hour. So there's many places that they are being produced. These are two samples of people being produced. But the key here is that not only who is producing it, but the quality of what you are producing and if it fits your needs. For example, in the sample that I put with the precision application of biochar, you need a specific shape and a specific density. Because that's the other thing. There's many densities, and many times the biochars they produce really low densities.
Okay. And then the second part of my question, you mentioned it's very expensive to apply. Where does that expense sit? Is it the expense in actually producing the product, or is it to do with the application?
I think it's more. There's many things to do with applications because I think that there has not been the interest in, let's say, like real world agriculture. There's many ways to apply it. You can think about pellets, briquettes, but this one you want to apply to 1 ton an hectare. The problem of the biochar is that so many times it's not dense enough, so you cannot just spread it on the fields. But I think the bigger problem is the cost. So there's many people, depending where you are and the quality that you have, but prices could be really high. Could be like more than 500 tons an hour or even more than that. There's people talking about 1,000 tons an hectare, a ton, and maybe they are talking about applying 2 tons an hectare. So that for a farmer is impossible.
Mm,
Of course, if you make the numbers, it may work for 100 years, but who is going to do that for 100 years?
yeah.
So that's why I'm proposing that maybe there's other routes at lower quantities where we can implement it here and now, the biochar.
Okay.
So start with baby steps.
Yeah, yeah. Okay. Uh, Andy Marchant, you have a question. Do you want to unmute yourself and ask?
Right. Yeah. Just a question about syngas, which you mentioned in passing, and you referenced this as being a significant element of the economics, which I can understand. But my experience, I'm sure yours, is syngas can be quite tricky in terms of low CV and things like that. Could you just say a little bit more on your experience of this? Anything relevant?
Yes, yes. You touched mm, the weakest link. You touched that. Managing syngas is very complicated. So more when we are talking about slow pyrolysis, it complicates everything. When you are talking about, for example, gasification, I think last year I went to see a plant in the Netherlands where they produce like a really clean gas, and I was thinking, oh gosh, what is this? But it requires really pure biomass, like wood pellets, really clean and a really specific process, really low yields because basically you gasified half of your biocarbon. But it is true when you are producing biochar through a slow pyrolysis, TARS is a big problem. And the other big problem is that one thing is when you are running that pilot plant, and then suddenly you produce a plant feeding 4 tons an hour of biomass. Suddenly you have so many problems. You don't believe that even when you're feeding a dry product, the pyrolysis reaction produce water, and you don't believe downstream from your syngas the amounts of water that you might have there. So there's two solutions for that. You either clean it, being really careful with the tars, because also you produce like heavy tars that they're like almost like stones when it cools down. Or you can just burn it directly and use these combusted gases for steam production, for example, or for other thermal processes like drying. But you are right. TAS is a big problem and is one of the weakest link for pyrolysis. But you have to use them, otherwise the sustainability of the project and economically is not going to work. I don't know if I replied to your question.
No, thank you. I'm just glad I'm not alone in having problems with this.
Yeah, but there's ways to solve it. There's plenty of
Yeah,
ways to
thanks.
solve the pyrolysis, but is one thing that it needs full attention and full focus. Yeah,
Okay.
totally agree.
Declan, you have a question?
That is very good, John. The It's a surprise, and as Charlie said earlier, that not much we've heard about it, but it seems to have a lot of good things going for it. Um, Applying it with the urea obviously gives some hope of development, so you can do a small bit of research on your farm or whatever. Can pellets is the word it was. You said it's in pellet form. Can it be applied by the standard farm equipment, or would you need to modify the farm equipment?
So in the sample that they put there, I think they use a standard maize planter or seeder. And normally you have two places where you can put fertilizers or whatever, and it was like a standard one that they got it, I think, from Spain. I was not involved into that, but I read what they did, and yes, you can apply for the collocation. You can apply a standard equipment that is out there. If you want to apply tons an hectare, you need to work on the form of your biochar because it could be very powdery and it creates many problems. So you need to densify your material.
Is that something the farmer would have to do?
I mean, no, because it will be complicated for the farmer.
Yes.
Unless you mix it with compost or with manure, and then it will be attached to your manure. Um,
Okay. Okay.
you need to pelletize or briquette it. Somebody has to do it for you. If you
Yeah.
want to put it concentrated, but for a standard farmer, you can mix it with the standard compost or the compost that they are using or the manure at different quantities. It will help the composting of the manure, for example. It has like an incredible effect.
Right.
Even in like my garden compost, when I apply biochar, it catalyzes the compost reaction like mad. Helps a lot for the composting.
So it gets complicated because at one time you say it's too expensive, so we want to drill it in with urea, but now you're saying there's a possibility that you could mass spread it with slurry or compost or
Yeah,
something.
it is possible. The problem of that is that it's going to be expensive.
Yes. Yeah. No, it's
So
okay. No, because
no, I think so. Let's say that the more traditional way is to spread it in the field. But what I'm trying to say here is that biochar will be expensive. Better let's apply it with precision tools
yes.
to
Yeah.
make it the best and using the minimum of biochar.
Yeah.
But
Okay.
using it,
Yeah, I understand that. That's good. Thank you, Juan.
you're welcome. You're welcome.
Are the financial benefits, how am I asking this? If you, in terms of producing the biochar,
Yeah.
is there any financial gains that the company producing biochar can get from people supplying the waste material, i.e., paying for waste disposal?
So there's two things. One is the potential gate fees that you can get from garden waste, for example.
Mm.
And the other one is there is voluntary market for carbon credits with biochar. So the producer can apply for this. So it's a cost per ton of CO2. I don't know what's the value now. It's between 100 to 200 pounds a ton of CO2. And that reduced the price. But still, it's going to be a few
Mm.
£100 per ton of biochar. Um, the market is progressing. The voluntary market for CO2 credits in biochar is developing, but it is well established. So I think that's one of the major incentives. So there's two routes. One of them is a potential gate fee for a biomass waste, and the other is the carbon credits. The problem with the waste is that you will finish with a lower quality product, more problematic to apply. You need further processing. So you will increase the cost of the processing. For example, if you use like an olive stone, so you can directly pyrolyze it, and that's the sample that I put in there for the maize planting. That's a direct olive stone that it's been used. But that material is very expensive. But at the end, you can use 50 kilograms an hour. If you use a lower quality, maybe you need to use a higher quantity and further processing the material. Like agglomeration. Agglomeration is also key in all of this.
Yeah. Okay. Thank you. And then you mentioned about the use of it in the building industry. Could you expand on that a bit?
So this is really trendy now. Many people is working on it. We are also working into that, and I decided to work into that because I'm seeing biochars that they cannot be used for agricultural use for because maybe they're coming from biomasses that you don't want to put. There's too many risks. For example, the organic fraction of the municipal solid waste. So you don't want to produce a biochar there and put it into a soil. But you can use it as part of the concrete and to store the CO2 there. Again, there's positive and negatives. There's a project now using the same material that I showed you there, that they are adding also the biochar in asphalt for tarmac production. And that way you apply a low percentage of the total mix, like let's think about 2%, 5%. And with that carbon that is stored in the biochar, you abate the emissions of CO2 of the operation of the application of the tarmac. Also the same thing with the concrete. You can mix it with the concrete. There's many working lines with that. But again, depending on the quality of your biochar, you will have one effect or another.
Yeah. So it's the cost to capture the carbon and bake it in is
Yeah.
the fundamental
So
challenge, isn't it? Yeah.
basically, you abate the CO2 emissions of the cement production and even the steel that you use in your concrete. You could abate them with the biochar. But there's many technical problems there because sometimes the biochar could help to the properties of your concrete. Other times it's the other way around. It could reduce the strength of your concrete.
Mhm. Okay.
It is not straightforward either.
Yeah. Okay. Well, any more questions from anybody? There's nothing in the chat.
I mean, this is a new process. The implementation is just starting. There's many unknowns, and as I told you, there's other farmer, the same farmer that tried with the 50 kilograms an hour. I think this year is trying with 200 kilograms an hour, increasing the dose, but in wheat and without irrigation.
And that's in the
So
UK.
no, that's in Spain again. So,
Spain again. Okay. Yeah.
but the conditions over there, there's really dry spring. So let's see what's happened there. So many times with biochar, if you have drier conditions, the effects they multiply because one of the things that has the biochar is that absorbs water. So it stores the water in the winter and then release it during the spring or the summer.
Mm.
It has that beautiful. So not all the biochars works for the same soils or the same conditions or different crops.
Okay. Yeah,
Thank you.
so thank you for that fascinating presentation. It's something I don't know anything about, so really interesting. So it's very much appreciated. Thank you everybody for joining us, and I hope you'll join us for our next lecture on the 14th of July, where we'll have Professor Kiran Toto Maharaj from the Royal Agricultural University, and he's going to talk about water resources and sustainability. So all that's left to say is thanks again, and we'll see you next time. Bye bye.